Okay, so now let us consider a somewhat new viewpoint of these channel coding schemes. And this viewpoint actually makes use of the linear algebra that you all are familiar with. And so specifically, we will see that the parity check equations for the single parity check code and the repetition codes and several other codes. So we'll be able to put them in a matrix form. And so to be able to do so, what we are going to do is we will start taking the input, which is this going to be this vector m, and the output, which is this vector c, of the channel coding encoder. Both of them we will be taking them as vectors. And so this m is a vector of k bits, where k is the number of information bits that is incoming to the channel encoder, and C has total of n bits, which are the encoded bits. And both these vectors m and c, we will make them to be tall vectors, which have the dimension of, in case of m, k cross 1, and in case of c, n cross 1. And these are binary vectors, just zeros and ones. And so that is kind of the first step that we will do to start going on this linear algebraic path of understanding channel coding. Now, over next few slides, we are going to start describing M and C through some matrix products. And so you're going to see this matrix products in the next slides. Now, one thing that you have to remember is that everything in this matrix equations, everything is binary and everything is modulo 2. All the matrices are binary, the input is binary, the output is binary. Obviously, the input is M and C, output is C, which we already said that these are binary vectors, but even the matrices are also going to be binary. And not only that, when we show the matrix product, they are not the ordinary standard integer valued matrix products, but at the end we take modulo 2 operation so as to make sure that the result of the matrix product is also binary valued. And so this entire algebra is called Galois field over two elements, zeros and ones, GF2. You may see references to GF2 in some textbooks. Galois field is an advanced abstract algebra topic, advanced topic of the abstract algebra, and we won't go into that. But you are, I think one interesting thing is for you to see the history of this Galois field. The spelling is Galois. It is pronounced as Galois, but the spelling is Galois. And the fields are named after the inventor of the field, Galois. He was a Frenchman, I think, and he died at a very young age. But he was a genius mathematician, and before his death, he came up with this entire theory of abstract algebra. You can do a search on Galois, and you will see the history behind his life and his death. A very interesting personality, and what he has developed is considered to be an amazing development of mathematics. So there is a whole lot of theory behind that, but we are going to see just the tip of that theory, which is encapsulated over in this few bullet points, where we say that everything is binary, and wherever summations and multiplications are involved, ultimately we take modulo 2 operation and turn them into the binary result. Now, if we consider some advanced techniques of channel coding, these vectors and matrices are not necessarily binary valued, but and that is where the real power of the Galois mathematics comes into play. But in this introductory class, we are not going to be considering non-binary elements of this algebra. Okay, so um, we are going to define two matrices. One is called the generator matrix and the other is called parity check matrix. The generator matrix is a size of n cross k. Remember, k is the number of information bits, n is the number of encoded bits. And the generator matrix is used to turn the information or the message bit vector m into the encoded vector c. And this is that matrix product that I had just mentioned. C is just a product of G and M. Now this product, as we saw earlier, is to be taken modulo 2, but otherwise, other than modulo 2 operation at the end, it is just it behaves exactly like the matrix vector product that you have studied in your high school mathematics course. So this is the equation for generating the encoded binary sequence C given the message sequence M, and here G plays the crucial role. Now you can imagine that G is a matrix that is going to be used at the encoder side, and so it is the encoder side generator matrix. It generates the code encoded binary sequences given the information bits. Now, similar to G matrix, there is something called the parity check matrix, and that matrix has a size of U cross N, such that if you take the product H times C, what you get is an all zero vector. And here U is N minus K, and it equals the number of parity bits or the redundancy bits that the encoder introduces. And this symbol denotes the all zero vector. Now this equation, you can see that it is more likely to be used at the receiver side, where the receiver gets certain coding sequence, a certain encoded sequence, let us say some binary sequence C, and it wants to see whether it satisfies all the parity checks, and that check is done by this parity check matrix that we will see later on. Basically, if for any received sequence, if H times that received sequence C turns into an all zero vector, then it means that the received sequence is a valid code word that the encoder could have transmitted. So these are the main two matrices, generator matrix and parity check matrix. Now let us take a look at some examples of this matrices. And so we'll start by considering the rate n-1 and SPC code. And so remember, for this code, the number of information bits is n-1. This code introduces only one parity bit, and so U is equal to 1. And the output of this encoder is n bit long, and so therefore these are the parameters of the code. Remember, we have studied SPC code earlier. We'll just flip through the slides. It is right here. This is the description of the SPC code. Number of message bits is n-1. There is U equal to 1 parity bit, and therefore the number of coded bits is n. Okay, so that particular scheme, we are now going to cast it in terms of this G and H matrices. Okay, so first we will talk about the parity check matrix for this SPC code, and you can imagine that the parity check matrix is a matrix of all ones. Basically, all that the parity check matrix does is it takes the inner product of this all one horizontal vector with the n cross 1 C vector, and that result should be a 1 cross 1, meaning it should be just a bit, and the value of that bit better be 0 if C is a valid SPC code word. So this is H times C is just a fancy way of describing the single parity checking that the receiver would do at the receiver of the SPC code. So H times C is equal to 0. In this case, 0 is just actual 0. It's just a scalar. It's not a vector here anymore. And H times C is nothing but a statement, a mathematical statement showing that all bits of C, if you add them up, they sum to value of 0, which by definition is what the SPC code is. And so this is an example of the parity check matrix right here. Okay, so let us stop here before we go on to discuss, or let us complete the generator matrix description, and then we'll take a break. Okay, so the generator matrix for the SPC code turns out to be an identity matrix of length k cross k. Remember, k is equal to n minus 1. It is the size of the information bits. So on the top of this G matrix is just an identity matrix, and at the bottom there is a horizontal vector of all ones. It's 1 cross k vector, and it is nothing but just all ones over there. Now if you think about this, this form of G matrix makes a lot of sense, because now when you take the product G times M, because of this identity matrix at the top, what will happen is at the output all these M bits are going to appear just as is. I mean, they are just going to come out without any change. So the first k equal to n minus 1 bits of the product G times M are just the message bits, which is what happens in the SPC code. The last bit is the parity bit that the encoder has to introduce, and the way the encoder calculates the parity bit is by summing all of the k message bits, and so that is exactly what this last row of G does, because it is a vector of all ones. When you multiply that with the vector M over here, you will get just one bit, which is modulo 2 sum of all of the message bits. And so G times M exactly gives us the SPC code. First n minus 1 bits are simply the message bits, and the last bit, nth bit, because of this 1 cross k vector of all ones, is nothing but the parity bit that the SPC code introduces.